MBSim implements common Modbus function codes. This section uses the Moxa IO-logic E1242 point table for the demonstrations. This point table includes coils, discrete inputs, holding registers, and input registers. These include read coils hex 01 and read discrete inputs hex 02, as well as read holding registers hex 03 and read input registers hex 04. It also supports write single coil hex 05 and write single holding register hex 06, plus write multiple coils hex 0f and write multiple holding registers hex 10. There are also two less common holding register functions, mask write register hex 16 and read/write multiple registers hex 17, which writes first and then reads in one request. Every demonstration uses the Modbus address from mappings.start address in the point table. Do not use reference addresses such as 30001 or 40,001 shown in PLC software directly as request addresses. We recommend the free, open-source Modbus tools as the master debugging tool. It supports common modes such as Modbus TCP and RTU, as well as hex 16 and hex 17 used here. I will put the Modbus tools repository URL in this chapter's pinned comment. First, let us demonstrate the coil area. Here we use DO0 status through DO3 status, starting at address 0. First, use hex 01 to read 4 coils. The 4 coils are packed into 1 data byte. Here, all 4 values are false, so the data byte is 00. Then we obtain the master request frame for reading these 4 coils. Send the request frame in the Modbus master tool and receive MBSim's response. Its data parses to 00, confirming that DO0 status through DO3 status are false. Tip: you do not need to copy the RTU frame's CRC. Modbus tools adds the CRC automatically. Second, use hex 05 to write a single coil. Write DO0 status at address 0, setting it to on. Third, immediately use hex 01 to read these 4 coils again and confirm that DO0 status is now on. Fourth, use hex 0f to write multiple coils. Again, start at coil address 0, corresponding to DO0 status, through DO3 status. You can write 1, 0, 1, 0. Fifth, use hex 01 to read these 4 coils again and confirm the batch write result. Next, let us demonstrate discrete inputs. The discrete input area is read-only. Here we use DI0 status through DI7 status. Use hex 02 to read 8 discrete inputs starting at address 0. Now let us demonstrate input registers. The input register area is also read-only. Here we use AI0 scaled value through AI3 scaled value, starting at address 520, and read 8 input registers. Because every point is F32, each point occupies 2 registers. Back in the MBSim table, you can see each point's raw and value. Raw is the original value after the point is mapped into the Modbus data area. It may come from 1 bit, 1 register, or a combination of multiple registers. Value is the business value after conversion by MBSim according to the point table. Finally, let us demonstrate holding registers. For a writable point, if its write behavior is accept and hold after a master write, MBSim accepts the write and retains the new value. Here we use DO0 pulse count through DO3 pulse count, starting at address 36. First, use hex 03 to read 4 holding registers and inspect their current values. Then use hex 06 to write 1 holding register. Write 100 to DO0 pulse count at address 36. After writing, use hex 03 to read the same holding register range and confirm that DO0 pulse count is now 100. Next, use hex 10 to write multiple holding registers. Start at address 36, corresponding to DO0 pulse count, through DO3 pulse count. You can write 100 billion, 200 million, 300,000, 400. After writing, use hex 03 to read the same holding register range and confirm the batch write result. Next, let us demonstrate hex 16, mask write register. Use holding register address 36, which corresponds to DO0 pulse count. We already set it to 100, or hex 0064 in hexadecimal. Set in mask to hex FFFE and or mask to hex 0001 to set only bit 0. The result becomes 101, or hex 0065, while all other bits remain unchanged. After the mask write, read it back with hex 03 to verify the result. Finally, let us demonstrate hex 17. It writes first, and then reads multiple holding registers in one request. We still use the 4 pulse count registers starting at holding register address 36. One request writes 11, 22, 33, 44, and reads back the same 4 holding registers. We have now demonstrated single and multiple holding register writes. Here is an example of a rejected write. DO2 pulse off with maps to holding register address 70, but the point table defines it as read only plus reject. When hex 06 tries to write 100, MBSim returns exception PDU 8602, and the point value remains unchanged. A write is accepted only when the area is writable, access is read-write or write-only, and write behavior equals accept and hold. Use read-only plus reject for normal read-only measurements, and read-write plus accept and hold for read-write controls or set points. Now let us look at data conversion. Raw type determines how register words are decoded, while transform type determines whether the decoded raw value needs engineering conversion. Numeric points in this MBSim point table mainly use transform type equals identity, meaning no scale, offset, or expression conversion is applied after decoding. For example, AI 0 scale value max has raw type equals F32 and occupies 2 consecutive input registers. MBSim combines the registers using the current byte order and 32-bit word swap setting, then interprets them as an IEEE 754 single precision float. Here, scaled is part of the point name and meaning in the device protocol. It does not mean MBSim applies an extra scale and offset conversion. For a fixed scale and offset, use transform type equals scale and offset. For example, un equals raw asterisk scale plus offset. For complex conversions with conditional logic, use transform type equals expression. Continue with MBSim iologic E1242 read-only write reject test sim to x l sx. 2 demonstration points have been added. An expression point requires both read expression and write expression. The next 2 points emphasize the read and write directions separately. Demo expression read maps to input register address 600 with an initial engineering value of -12.3 degc. Its raw register value is 65,413 or hex FF85 in hexadecimal. Send a read request. The response register is FF85 and read expression interprets this unsigned 16-bit raw value as -12.3. Demo expression write maps to holding register address 601 and is configured as read-write plus accept and hold. Enter the engineering value -12.3 in the master request frame generator. Write expression encodes it as 65413 or hex FF85. After sending the write request, the table shows raw equals 65413 and value equals -12.3. This shows that read expression converts raw to an engineering value when reading, while write expression converts an engineering value to raw when writing. Finally, let us look at the Endianness settings. First, look at bit order. To make the difference clear, 2 simulator instances are prepared. Both use the same point table and station ID, but listen on different TCP ports. Except for bit order, all other settings are identical. The bit MSB instance uses MSB first, while bit LSB uses LSB first. Here, select DO0 all status from DO00. It maps to holding register address 32, with a bit offset of 0. Both instances set this point to true, giving a raw value of 1. First, look at the bit MSB instance. With MSB first, logical bit 0 is encoded in the register's most significant bit, so register words shows hex 8000. Now switch to the bit LSB instance. With LSB first, logical bit 0 is encoded in the register's least significant bit, so register words shows hex 0001. Both instances show bits 0 through 0 equals 1 in bit slice. Their point and raw values are also identical. Only the encoded position of logical bit 0 within the 16-bit register changes. Next, look at byte order. Again, 2 simulator instances are prepared to make the difference clear. Both use the same point table and station ID, but listen on different TCP ports. Except for byte order, all other settings are identical. The byte B instance uses Big Endian, while byte LE uses Little Endian. Here, select D00 pulse count. It maps to holding register address 36 and has the U16 data type. To avoid an unrelated write operation, the point table sets this point's default value to 4660 or hex 1234 in hexadecimal. After both instances start, value and raw are both 4660. First, look at the byte B instance. With Big Endian, the two bytes are encoded as 1234, so register words shows hex 1234. Now switch to the byte LE instance. With Little Endian, the two bytes exchange positions and are encoded as 3412, so register words shows hex 3412. The logical and raw values are identical in both instances. Only the byte order within one 16-bit register changes. Next, look at word swap, 32-bit. Again, two simulator instances are prepared. Both use the same point table and station ID, but listen on different TCP ports. Both keep byte order set to Big Endian and disable double word swap, 64-bit. The only difference is that word normal disables word swap, 32-bit, while word swap enables it. Here, select AI0 burnout value. It has the F32 data type and occupies holding register addresses 560 and 561. To avoid an unrelated write operation, the point table sets this point's initial value to 3.14. After both instances start, value and raw are both 3.14. First, look at the word normal instance. Without a word swap, the register word at address 560 is hex 4048, and the word at address 561 is hex F5C3. Now switch to the word swap instance. With word swap, 32-bit, enabled, the two 16-bit register words exchange positions. Address 560 becomes hex F5C3, and address 561 becomes hex 4048. Both instances represent exactly the same engineering value. Only the order of the two 16-bit register words that form this 32-bit float changes. Finally, look at double word swap, 64-bit. This setting affects only 64-bit data that occupies for consecutive registers. It swaps the first and second 32-bit double words. Before it is enabled, the four register words can be written as W0, W1, W2, W3. After it is enabled, the order becomes W2, W3, W0, W1. The current Moxa point table has no U64, S64, or F64 points. Therefore, we will not create comparison instances or change point tables here. We will only explain what this setting does. In a real project using 64-bit integers, accumulators, or double precision floats, check the device manual to confirm the double word order. If master reads or writes produce incorrect results, first check area and start address. Then check register count and bit offset. Next, check raw type, transform type, read expression, and write expression. Finally, check the Endianness settings here.